so the basic challenge in the field of thermoelectrics are to find materials that conduct electricity very well, but do not conduct heat very well. And that defines the efficiency of the thermoelectric, how efficiently it can harvest heat and turn this into electrical voltage. Now, past thermoelectrics had a relatively low efficiency, which made them suitable for niche applications, but this new research that's been done in collaboration with the University of Wollongong has discovered a new generation of thermoelectrics that combine these topological materials with embedded nanoparticles. And that opens up a range of exciting new possibilities. And this research will be looking at how these materials can be exploited in a range of contexts. This can be, from energy generation in an industrial process all the way through to providing flexible thermoelectrics for emergency lighting in a mining scenario.
A thermoelectric material is one in which we can transfer waste heat into electrical energy through a temperature gradient in a material. Now, this research is being performed in collaboration with our colleagues at University of Wollongong, who've developed a new generation of thermoelectric material. Now, Australia is well placed because we have an abundance of sunlight and heat, and we have a number of industries that generate a lot of waste heat as a byproduct. And so with these new thermoelectric materials, we can hopefully harness the heat generation into electrical energy.
Okay, well, topological insulators are a new type of material that was only discovered in the past decade. And these materials have a very unique property that the electronic structure of the surface is different from the bulk. And what that means is that there are states of the surface that conduct electricity even when the bulk is not conducting electricity. So the interior of the topological insulator has a very different property from the surface. And overall, these materials tend to be very, very electrically conductive, which is exactly what we want for thermoelectric. The analogy we sometimes use when we're explaining this to school children is kind of like a chocolate bar, right? It's a chocolate bar wrapped in aluminium foil. The chocolate itself won't conduct electricity, but the aluminium foil will. But what makes a topological insulator so special is this is really happening on a much finer atomic scale. So as you subdivide the topological insulator and cut it into smaller and smaller parts and create new surfaces, the new surfaces are always electrically conductive. And that's a special feature of the underlying quantum mechanics in this case, which makes these materials very interesting.
And one of the ways that we're going to investigate these is by looking at their phonon spectrum. Not photon, but phonon. Now, phonon is when the atoms in a material will vibrate and oscillate coherently. And in doing so, they can transmit information through a material. So they could transmit sound, for instance, or heat. And in this case, in our thermoelectric materials, we want to prevent heat being transmitted through our materials. And so this is where the inclusion of the nanoparticles will help to block the phonon propagation through our materials.
So neutron spectroscopy is uniquely able to tell us how the atoms move in a solid or even in a liquid. It tells us how fast they move and the displacements. And this is very important for these thermoelectrics because it helps us understand how heat moves through these materials. As Gary mentioned before, heat is moving through phonons, which are these type of vibrations that travel through a solid. Phonon comes from the Greek word phonon, or phono, I think, which means sound, right? And so this is closely related to how sound travels, but heat travels at much higher frequencies as a general rule. And these are the frequencies we can probe with neutron spectroscopy. Yeah, we're really excited by this project. I mean, we've been working on the basic science for a few years here at ANSTO using the neutron spectroscopy instruments, and we started to see these patterns emerging, and now we've taken these ideas and we've applied it to a new, more commercially relevant set of materials. And I think this will open a lot of new, exciting avenues in the coming years. And I really think that having the infrastructure at ANSTO gives Australian researchers a bit of an edge in this area.